Okay, thank you. Paul Blase from Space Initiatives, Inc., along with Marshall Eubanks, who is present, and together with the Institute for International Studies, we put together a proposal for the NASA NIAC program on how to rapidly respond to targets of opportunity, such as the Apophis asteroid close encounter. So Breakthrough Starshot, if you've heard of that, is a project to develop laser-driven sailcraft for a far future, 50 years or so, mission to Alpha Centauri. This would be comprise a fleet of several hundred sailcraft launched with a multi-gigawatt laser array. And our group, Space Initiatives and I4IS, have been working on swarming and communications techniques for getting data back from such a fleet of sailcraft. So we thought a laser sailcraft is an inexpensive and very rapid response way of getting a probe to short notice targets, such as asteroids, comets. Eventually, you could explore Kuiper Belt objects as they're discovered. Definitely targets like Oumuamua that give practically no notice at all that they're coming through. So what we're proposing here is a derivation of the sailcraft built using existing technology, admittedly bleeding edge, which could launch one or two sails on a near-Earth course with notice times of days. So the Apophis asteroid is a near-Earth asteroid that will pass within 30,000 kilometers of Earth in 2029. So using this encounter as a sample precursor mission, we would deploy a fleet of 2, maybe 3 sailcraft from a sounding rocket, such as the Black Brant, use a laser array in the tens of megawatts, which is achievable using current commercial fiber lasers, for a total mission duration of about 24 hours. 10 megawatts will throw a 1 gram sail up to about 35,000 kilometers. And then it wouldn't put it into escape trajectory, it would fall back down. The science goals are imaging and basic science. These would be flybys. Although we wouldn't do it for Oumuamua because the surface studies people want to not touch the surface, we could plant a transponder on an asteroid, and we could possibly carry active radar transmitters or receivers to work with ground arrays on precise orbit determination. So the basic sail design is shown on the right using ultralight 3D printed metamaterials. Basically the entire probe is 3D printed. What we propose to NIAC is actually the mechanism for how you 3D print metamaterials with micron scale resolution that are a meter wide. So the top side contains sensors and photovoltaics. The bottom side is a very high efficiency reflector. Again, using optical metamaterials, it can be self-stabilizing in the laser beam. and it could also stabilize for a possible return of the probe back into the Earth atmosphere. If things light enough, it would simply deaccelerate and waft down. We were actually considering one scenario where one probe would impact an asteroid and the second one would fly through the dust plume and collect dust, similar to NASA's aerogel probes. So sensors would be basic visible infrared cameras, spectrometers, magnetometers, and RF sensors. Metamaterials used are advanced ultralight, ultra-stiff materials. These are made in a couple of ways. The favorite one at present is doing 3D printing with a polymer. And as you can see on the figure on the left, these are metamaterials, which are structures of structures. And at the smallest level, you're looking at tubes that are micron or less in diameter. So you 3D print these in a polymer, electroplate it with nickel, dissolve out the polymer, and you have a very stiff material. And you can actually tailor the mechanics of the material for thermal transmission, rigidity, and other desired effects. Similarly, you can make optical metamaterials, which give you flat lenses and other interesting effects like the ability to self-center in a laser beam. For this sample, proposal, we put in magnetorquers to allow attitude adjustment using the Earth's magnetic field, which would allow you to rotate your imaging and tack. It would just use RF data return, although for the Alpha Centauri mission, we're looking at optical means, and several options that you could incorporate into such a probe. Launch Laser Array is going to be a project in and of itself. In order to get the velocities we need, we're using 17 to 20 megawatts of power.
2 minutes, Paul.
Thank you. 10 or 15 coupled industrial strength fiber lasers, each with its own telescope. So this would, when the craft has just been deployed and it's reasonably close, give you about 5 G's acceleration, and which would kick you up to 35 kilometers apogee, which would allow a flyby of the asteroid at closest approach. We're currently looking at launching off of Wallops Island because that has the required range safety for the laser. Also happens to have a sounding rocket launch facility close by. Another possibility would be putting it out in New Mexico or one of the desert regions where the weather might be clearer, but this picture of the Earth position is accurate. So we would actually get a good view from the middle US later in the flyby, in the Apophis flyby. So that's just what the timing of the whole scenario looks like. April 13th to 14th, 2029, and the elevation angle from Wallops Island. So the ideal situation is we're looking straight up and just sending this thing straight vertically. Again, we're not trying to go into orbit. This is a pure ballistic flight. Base mission, then 2 sailcraft launched in the Black Brant. We released one fairly early and the other at the Black Brant's apogee of 1,500 kilometers. So the laser array boosts the first one and then the second one up to 30,000 kilometers. So that number 1 encounters it during the descent and number 2 during the ascent. Backup.
Paul, thank you. Sorry, Paul. We have to move on to our next speaker. But thank you so much for your talk, and we'll be sure to ask you questions during the discussion time.
Okay, thank you very much.